Good morning, everyone. Thank you, Thomas, for that very kind introduction. I was ready to crawl behind the podium back here. So it's my pleasure this morning to give you a current snapshot in where we are today in searching for atmospheres around rocky planets. So you've heard many times now that Earth-like planets are extremely common in the galaxy. If you have 100 billion stars and say approximately half of those have a rocky planet orbiting them. Many of those planets are both the same size and roughly the same temperature as the Earth. And so the potential for learning about the origin of life on other planets is just enormous. However, a huge question is, what do we really mean by Earth-like? So when we discover these planets, we measure their masses, we measure their radii, but we don't know anything about their atmospheres, and that can make the difference between a nice habitable planet like the Earth with its abundant water and oxygen, nitrogen, the building blocks for life, and an airless, bare rock like Mercury. And Earth's atmosphere only contributes a fraction of a percent to the total radius, so this is below the level that we can measure with mass and radius measurements alone, and so what we have to do is go and characterize the atmospheres of the planets directly. We heard a little bit from Didier about how this works yesterday. I'll give you a refresher this morning. So the basic idea is that for planets that periodically pass in front of their host stars, these are transiting planets, when the planet is in front of the star, a little bit of the starlight can filter through the planet's atmosphere where it could be absorbed and scattered. Different molecules have different opacity signatures, so some molecules are particularly opaque at certain wavelengths. It provides us a unique chemical fingerprint that allows us to infer the atmospheric composition of the planets. To make this a little bit more intuitive, here's an example of our own Earth as viewed from space. You can see the beautiful blue Rayleigh scattering signature from Earth's atmosphere. This is optical light, so what we see with our eyes. But if you move to the infrared, this is what the Earth looks like. And so you can see that that little Rayleigh scattering signature is gone, and Earth appears a little bit smaller. But if you move just 1 micron farther into the infrared, this is 9.6 microns, you hit the ozone band. Ozone is very strongly absorbing at this particular wavelength. And you can see, by going back and forth between these, that Earth is just a little bit bigger at 9.6 microns than it is at 8.6 microns. Now, this is very easy to see if you are so fortunate as to have a satellite orbiting your planet and you can take nice pictures of it. If we want to do this for exoplanets that are tens of light years away, it's of course much, much more challenging. So for many years, we were practicing this technique on Jupiter-sized planets. This is one of the best examples as of about 5 years ago. This is the transmission spectrum of a hot Jupiter. You can see planet radius on the y-axis and wavelength on the x-axis, so going from blue to red from left to right. And there's a beautiful absorption feature from water. That's the arrow drawn to the middle. And if you're an expert in this field, you recognize that as water as easily as I would recognize my own mother walking down the street. So this is a very, very distinctive absorption feature from water. And one of the things that we learned from studying these Jupiter-sized planets is that water is extremely common. In some sense, this is not a surprise, because after hydrogen and helium, carbon, nitrogen, and oxygen are the most abundant elements in the universe. At the temperatures and pressures that we're observing, if you have hydrogen and you have oxygen in chemical equilibrium, they prefer to be in the form of water. And so while Jupiter-sized planets we don't think are habitable for a variety of reasons, this is a good sign that water is everywhere in the universe. And so if it can make it into these large planets, perhaps it can make it onto small Earth-sized planets as well. Okay. We heard a lot about the James Webb Space Telescope yesterday. I'll put my own spin on it here. So This is the most advanced thing we have ever put in space. So JWST was in the making for almost 3 decades, so I feel extraordinarily privileged that I happen to be born at the correct time to be able to take advantage of this amazing facility. Here we have an animation of what happened to the telescope after it was launched. So Thomas Zurbuchen yesterday said that 20% of the risk was the launch, 80% of the risk was what happened afterwards. This is what he was talking about. So here you see the sun shield unfolding. We have to block out the heat from the sun in order to observe very faint infrared signals. This is what JWST was designed to do. You see it unfurling here. Just before launch, I read an article that said that there were, in this complicated unfolding process, there were 300 single-point failures, where if any single one of those went wrong, the telescope would not have operated as intended. So I think for lay people and the public, this was really exciting. For me, where the science I want to do really depends on this telescope, I was a nervous wreck. I was so worried. But it came together perfectly. Here you see the primary mirror unfolding. Now, I should say the reason the telescope was folded up is that it's so big that it couldn't fit fully assembled inside a rocket. So they had to fold it into like an origami telescope that then unfolded after launch. And it came together beautifully. We were so lucky. Okay. So everybody loves a good before and after. I'm coming back to the spectrum I just showed you. This is a hot Jupiter planet. I'm going to zoom in to this red box. This is the infrared 3 to 5 micron region, and show you our view prior to JWST. That's here. And now after. Look at that. I have seen this a million times and it never gets old. In fact, one of my colleagues who's a theoretical modeler of exoplanet atmospheres, I asked him what he thought about this. And he said, well, honestly, like it's so perfect it looks fake, so I'm not excited. And a typical theorist, like he's not happy when the data is bad, he's not happy when the data is good. But in any case, this is the first detection of carbon dioxide in the atmosphere of any exoplanet. So it sticks out there like a sore thumb. It's extremely clear. When we saw this feature, we actually struggled to quantify the detection significance because it was so high it broke the numerical precision of all of our codes. Okay. So now, thanks to this enormous advance in observing capabilities, so JWST has 10 times the collecting area, 10 times the wavelength coverage, 10 times the spectral resolution, 10 times the pointing stability of any telescope coming before it. So Hubble was the standard bearer prior to JWST, and JWST is now 30 years more modern and provides a revolution in our observing capability. And we can now push to small planets for the first time and have the potential to get really detailed measurements of their spectra. So I will kick us off with the smallest planet so far with a detected atmosphere. This planet is called TOI 270d. It's a little more than 2 times the radius of the Earth. It's a little bit hotter, temperature somewhere in the neighborhood of 380 Kelvin. And this is the transmission spectrum, and you can see labeled on this figure absorption features from a whole host of different molecules. Really strong absorption from methane, very clear features from carbon dioxide. We see water at the red edge between 5 and 6 microns, slightly lower significance, but we also think we're seeing photochemical byproducts in the atmosphere, so that would be CS2 and sulfur dioxide. So this is really volatiles galore. And with a spectrum of this quality, we're able to measure the mass ratio of different elements. And what we're finding for this planet is that the ratio of hydrogen to carbon to oxygen is approximately 3 to 2 to 1. So that puts our atmosphere at about 50% hydrogen by mass and about 50% carbon and oxygen. And importantly, one of the things we've learned from this is that if you have that much hydrogen in your atmosphere, your planet is not going to have a solid surface, because if you follow the adiabat down, the temperature and pressure get higher and higher, so that by the time you reach the rocky core, you actually hit it, it's in the form of a magma ocean rather than a solid surface. And so even though, while on paper, this planet looks pretty close to something that might be habitable, it's not that much bigger than Earth, it's not that much hotter than Earth, it's actually something fundamentally different. And now this still teaches us really important things about the delivery of volatiles to small planets. This is brand new, this just came out in the last 6 months, and so we're still understanding exactly where that carbon and oxygen come from in the atmosphere and what that means for the delivery of these materials to rocky planets. So I want this to stand on its own. I think sometimes these results are presented as like, maybe these are habitable worlds. I personally really don't think so. Maybe that's up for debate. That's something we could discuss over coffee. But it's already huge progress. We had no idea what these small planets really looked like prior to JWST. But what I'm really here today to talk to you about is planets that are truly rocky. We're looking for things that have a solid surface. And for these planets, one of the challenges in studying them is that we don't know if they have atmospheres at all. Like I said earlier, the atmosphere of the rocky planets in the solar system typically contributes less than 1% to the total radius. We can't measure that from masses and radii alone. And so we're left wondering, is there even an atmosphere to study or not? You hear a lot about searching for biosignatures and measuring the atmospheric composition of these rocky planets in great detail. But what I always say is you have to walk before you can run. And so our first question is just, which of these planets have an atmosphere at all? So one approach, my current favorite approach to answering this question, is to measure the heat coming from the planets themselves. And the idea here is that many of the planets we can study are quite close to their stars, so they're tidally locked. They have a permanent day side that's irradiated by the star, and a permanent night side that is in perpetual darkness. And for cases like this, as the planet moves through its orbit, different phases are exposed in turn. And while we can't spatially separate the planets from their stars on the sky, they're too close together, what we can measure is the planet's thermal emission, something like a phase curve that I'm showing here. What you're seeing now is the hot day side of the planet rotating into view. You can see the increase in brightness due to the increased thermal flux of the day side. Here's the secondary eclipse. The planet goes behind the star, and now the day side is rotating out of view. And we can use measurements like this to determine the climate of the planet. So how hot is it on the day side versus how hot is it on the night side? And to zero the order, this tells us the surface pressure of the atmosphere. The idea is that thick atmospheres are good at redistributing heat from the day side to the night side. So if you have a thick atmosphere like Venus, you end up with a day side and night side that have almost identical temperature. Whereas, if you have a bare rock, you have an maximally hot day side. You cannot get hotter than this, and a night side that's consistent with 0. Okay. So I know this is an audience that has a very wide range of backgrounds, so I've designed for you my personal atmosphere rating system that uses chili peppers. This absorbs everything we know about atmospheric dynamics and radiative transfer into a very simple model to interpret what we have measured so far. So a 3 chili pepper planet is going to have the hottest possible day side. This implies that it does not have an atmosphere because there's no atmosphere to redistribute that heat from day to night. And a 2 chili pepper planet is intermediate temperature, so you have to have some atmosphere that is helping to redistribute the heat. And finally, a 1 chili pepper planet is a planet, very special type of planet that not only has an atmosphere, but also has an optically thick level of carbon dioxide. And to briefly explain this, I think this can be confusing for folks because we think of carbon dioxide as something that causes greenhouse warming. That's true, that makes the surface hotter. However, we're not if CO2 is optically thick, we can't see down to the surface, and rather we're actually seeing a tippy-top upper layer of the atmosphere because the CO2 is so opaque we can't see deep down. And so up there, high up in the atmosphere, the temperature is actually lower. So if you see something that's very cold, that is indicative of carbon dioxide in the atmosphere. Okay. So where do we start? Most of the planets that we can study with JWST are somewhat different from the Earth and the Sun. They're orbiting very small stars called M-dwarfs, and these small stars are the most abundant type of star in the galaxy. The Sun is actually a bit on the large side, so typical stars are smaller. And not only are there more M-dwarfs, and these represent the most numerous rocky planets in the galaxy, the planets are also much easier to study because we're always making measurements relative to the star. So if you have a large planet-to-star size ratio, my job as an observer is much easier. So these are the ones where we start. And the first system that I'd like to talk about is TRAPPIST-1. We heard a little bit about this yesterday. As a reminder, this is a system of 7 rocky planets transiting a nearby ultra-cool dwarf star. It's only 12 parsecs away, something like 40 light years. 3 of the planets are potentially habitable. You can see that in the green band in this artist impression here. And one of them is a Venus analog, so almost exactly the same size and temperature as Venus. We heard from Thomas Buchan yesterday that the discovery of this system made headlines all over the world, but what I was personally most impressed by is it made it actually to the Google Doodle. So boy, were we excited. I think this was the single most hyped up planetary system. Everybody loves TRAPPIST. You know, as scientists, we're trained to be like objective and try to evaluate based on what we have measured, you know, what is physically true. But in my heart, I feel like this. Like, you know, these are rocky planets. They're so close. We can learn so much about them. We're really excited to see what they are. So one of actually the very first rocky planet observed with JWST was the innermost planet in the TRAPPIST-1 system. And I just want to take a moment and show you the raw data here. So this is the measurement of the total brightness, so planet plus star over time. You can see just a little dip right in the middle of this figure. That's when the planet goes behind the star, and the little bit of thermal emission that is coming from the planet is blocked. We're doing this way out at 15 microns, so in the infrared, that's where the contrast ratio between the planet and the star is the best. And just boom, there it is. This reminds me of some of the very, very first exoplanet atmosphere characterization from almost 20 years ago, where we did this for gas giants, for hot Jupiters. And in this paper, kind of as a nod to that past work, they picked the same plotting style, this kind of an old school type of plot, to mimic the pioneering work that was done for hot Jupiters 20 years ago. Okay, so here we are seeing photons from TRAPPIST-1b at a distance of 12 parsecs, so it's, we're looking at the planet as it appeared 40 years in the past, and here's my rating. So this is definitely a 3 chili pepper planet. The temperature of the day side relative to the maximum is 99%, plus or minus 5%. So this is as hot as it could possibly be. I wrote the news and views for this paper when it came out, and my headline was "Search for Distant Atmospheres Off to a Rocky Start." And this was a little bit tough because people are emotionally invested in these planets. We're rooting for atmospheres. And so I watched some of my colleagues go through like the 5 stages of grief. Like first there was denial. They're like, oh, maybe the data is wrong. Data is not wrong. Data is beautiful. There's anger. They're like, oh, you make this headline sound so glib, like, whereas I think at the moment we're in the bargaining phase to try to figure out, is there any possible atmosphere you could put on this planet and still be consistent with this? The answer to that is yes. Like you could, if your atmosphere is extremely thin and extremely carbon poor, you can get, within 2 sigma consistent with this measurement, but we're really starting to split hairs here, and it feels like bargaining. Like I think the Occam's razor would say the simplest hypothesis is that this thing is a bare rock, and if you're contorting yourself to try to find an atmosphere that is consistent with what we measure, you go for it. That's the process of doing science. But I think the burden of proof is really on proving that there is an atmosphere, not that there isn't one. Okay, so sorry to be the bearer of bad news, but that's where we are. The next rocky planet that JWST observed was also in the TRAPPIST-1 system. We now this time moved 1 planet further out to planet C. This is the one that is in some sense a Venus analog. So this planet is roughly the same size and the same temperature to Venus. And so our first guess was maybe it has a Venus-like atmosphere. Venus has about 100 bars of carbon dioxide, so about 100 times the surface pressure of the Earth. Carbon dioxide is considered an extremely plausible constituent of these atmospheres, of these slightly hotter than Earth planets. Not only is it outgassed from volcanic activity, but it's also very heavy, so it likes to stick around, it's stable. If the planet had a Venus-like atmosphere, it's certainly something that would be expected from our understanding of planet formation, and the atmosphere would be, we would not be surprised to see something like this. So, here's what we measured. So what I'm showing here is a measurement of planet to star flux, so the ratio of the brightness of the planet relative to the star. It's the red data point. You can see how primitive these measurements are, right? It's just a single data point, 1 spectral band. This took about 20 hours of JWST time. And compared to some models, we see that the planet is a little bit cooler than the innermost planet. But it's a lot hotter than we would expect for Venus. And so a Venus-like, a pure CO2 composition is really strongly ruled out. There could be a little bit of atmosphere on the planet, so this one feels less like bargaining. You can have, put like a bar of oxygen on there. As long as you don't have too much carbon dioxide in it, it can be totally consistent with the data. But still, I give this planet 2.5 chili peppers. It's pretty hot. And it's also being very actively followed up, so we'll get additional wavelength coverage. We're actually doing a whole phase curve. And so we'll know definitively whether it has a thick atmosphere or not pretty soon. Okay. Here is the family portrait as of last week. These are all of the measurements of brightness temperature that we have from JWST so far. There's 5 of them. So in classic astronomer fashion, I will make an enormous inference based on 5 data points with kind of big error bars, which is to say that the emerging picture from these measurements is that the rocky planets we've looked at so far are likely airless. So these things are all consistent with a bare rock, even pushing down to TRAPPIST-1c, which is the coolest planet in this plot. It's still consistent with a bare rock at roughly 2 sigma. A caveat here is that these planets are all fairly hot. So the hotter the planet is, the more vulnerable it is to atmospheric loss. And they all have these small M-dwarf host stars, which in some ways are quite different from the sun. These small stars are bright in the ultraviolet for the first gigayear of their lives, so they're really blasting their planets with high-energy radiation that can contribute to atmospheric loss. And so if you asked a theorist, is this result hugely surprising? I think most of them would say no, actually, that these planets, the lowest hanging fruit that was easiest for us to study first, are actually the least likely to have atmospheres. And it's extraordinary that we can measure this. as a test and a benchmark for these models. So I am still very optimistic. So I was hoping, when I agreed to give this talk, I was hoping that we would have a really firm detection of an atmosphere that I'd be able to share with you all. But that's not where we are, and that's how science goes. I think Thomas Verbuchen in his talk yesterday said that a lot of science is dead ends. I wouldn't say that this is a dead end, not by any stretch, but just that it's hard. I think, if there was a chance that these planets would be lousy with atmospheres and that all of them would have a lot of carbon dioxide and we could easily see it. And that's not the case, but we only just started. So there's only half a dozen of these planets that have been observed. There's 30 more that are coming in the next couple of years. As Thomas mentioned in the introduction, we just got 500 hours of director's discretionary time approved for exactly this science case. And so if there are atmospheres to be found, JWST is going to find them for this type of planet. And not only that, but airless planets are also an exciting scientific opportunity for two reasons. One of them is that even if we don't observe an atmosphere today, we can use that to rewind the clock to say how much carbon and oxygen the planet could have had when it formed. And so in the case of sorry, that's a typo. In the case of TRAPPIST-1c, we know that the planet formed with less carbon than Earth. There are a lot of uncertainties in that statement, so things that we don't know particularly well are how this brightness of the star has evolved over time, how bright it was in the ultraviolet early in its life. There's also big uncertainties associated with the outgassing rate, so how much carbon dioxide came out of the planet as it aged, and how that could have been lost over time. So I think this is going to be a really active area of research in the next couple of years to really understand, if you don't observe a thick CO2 atmosphere on a planet, what does that mean about exactly how much carbon it could have had? In addition to that, we can also start to study the surfaces of the planet. If there's no atmosphere in the way, you can characterize the composition of the rock on the surface of the planet. And so for one of these airless planets, we measured a thermal emission spectrum. It looks like this. This is unpublished, so please no social media. And what we found is that the surface of the planet is so hot that it's actually incompatible with all of the rocky models that we initially tested. And our idea was that to get the surface even hotter, you need to have a darker rock, so even more absorptive. And that's something that happens as the planet ages. If you have an old surface, it gets darker over time due to space weathering. And so what we think we're seeing is evidence for an extremely old surface, which means that the planet has not been volcanically or tectonically active for a very long time. So what we're seeing is like a stagnant lid of an exoplanet. And this is a completely open question in geology, like how often and under what conditions you expect plate tectonics. And here with exoplanets, we have a first data point to actually constrain the geologic history of the planet. So I'll leave you with another note of optimism. JWST, I would say, is extraordinary, but it is only the beginning. There's enormous enthusiasm in the astronomical community to study even more rocky planets. And there are two mission concepts under active development that would be capable not only of doing these type of transit observations, but also of directly imaging the rocky planets. To broaden the sample, you can actually take a picture of an Earth-like planet next to a Sun-like star, measure a spectrum, and search for biosignatures. So this is not something for today or not something for tomorrow, but over the next 20 years, and something that I'm really excited to get to work on. So with that, thank you very much, and I'm happy to take questions.